My name is Lateshia Terrell. I'm a senior majoring in computer engineering, set with a minor in mathematics, attending Bethune Cookman University in Daytona Beach, Florida. The title of my project is Unmanned Surface Vehicle for Environmental Science Applications. I was assisted in my research by my advisor, Dr. Calderon. I would like to draw your attention to the ferry. That's the world's first autonomous ferry, the Rolls-Royce Falcon. To begin with, the research being conducted on autonomous boats is fairly new when compared to the research being done on autonomous boats, on autonomous cars. It began in the 1500s, centuries before the invention of the automobile. Leonardo da Vinci designed a cart that could move without being pushed or pulled. Springs under high tension provided the power to the cart, and steering could be set in advance so the cart could move along a predetermined path. This device is sometimes considered the world's first robot. In 1970, the concept of autonomous ships was first introduced during Rolf Schnocknitz's book, Ships and Shipping of Tomorrow, where it mentioned that in the future, captains will perform their duties from onshore office buildings and vessels will navigate with the use of computers. Jumping a little bit ahead, I would like to draw your attention to 2015 with the Advanced Autonomous Waterborne Application Initiative, which was launched by Rolls-Royce in 2015. That project seeked to analyze challenges in different scientific fields related to autonomous shipping operation. It developed both autonomous and remote operation for ship navigation, machinery, and onboard operating systems. And in February 2016, a major advancement was made when LR published a guidance concerning cyber embedded ships deploying information and communication technology and shipping. And again, you can see a picture of the Falcon. Moving forward, the task, my abstract of the purpose behind the research in my project. During the last decade, artificial intelligence and robotics have advanced like never before. Today, robots are becoming a fundamental part of human life, such as surveillance, search and rescue, last mile delivery packages, and other applications. This research aims to develop an unsurfaced vehicle to perform surveillance mission, remote sensing, animal rescue, and trash collections. The proposed USV is designed using low-cost materials and will have propellers above the water surface to reduce its potential disturbance of underwater environment and organism. The USV's traction is based on electrical engine use. The steering is managed from the speed difference between the engines. It will have an electrical system compatible with different sensors. A navigation system is based on the use of cameras and GPS. A computer system is based on the use of embedded computers. The USV will be tested for implementing artificial intelligence algorithm focused on navigation and artificial vision to identify objects of interest in a controlled environment. So short answer, I'm trying to construct a boat that will navigate on its own through computer programs and other applications to search and rescue and identify water coastal conditions. So I hope you got all of that out of what I just said. Okay, where to begin? So when you're constructing a boat, like where to start? I mean, most people could start at like, I don't know, a marina, but I didn't. So I had to decide how am I going to start. And the first thing, how am I going to do my boat? So that's where I began with a propulsion. So propulsion is a word, it's a word derived from two Latin words, pro and per. Propulsion is to move or object forward. And propulsion is used because thrust is generated through an application of Newton's third law. Okay, so there's four main type of propulsion system: the propeller, the turbine, the ramjet, and the rocket. One type of propel system that, as you can see, I went with, and I'll explain why, is the propeller system. And the spilling propeller acts like a disc through which surrounding air passes. The yellow elliptical you can see on the screen, that is a schematic. The engine shown in white turns propellers and does work on airflow. So there is an abrupt change in pressure across the propeller, denoted by delta across the propellers. The pressure changes from delta P, so delta
Oh. Okay, I don't know what to do. Let's see.
In my
There she is.
in my abstract, in my my communications unstable. No. Hello. Okay, hopefully it's okay. But basically the other jet engines, they require a chemical combustion. So it's a full, it's oxygen based, and it has like byproducts of exhaust and things, and that we didn't want to use that to disturb the water. So we went ahead and went with the propeller system because it's above the water surface and it has less potential for disturbance of the water. And also we did some research, and jets and engines underwater can have a problem with seaweed affecting navigation. So that's the reason why the propeller system was chosen. Okay, so moving from there, I have a mechanism of how to move my boat. Now I have to construct a circuit of how to actually get that to operate. And I chose a ESC 30 amp brushless motor. I configured 2 different motors. I use hardware configuration in the circuit and also software design to isolate both motors so I can run them simultaneously or in unison together. Okay, the process, as also stated in my abstract, the main research, the aim of this is to make sure that it is accessible, that the parts are cheap, and this open source programming and platform, so therefore it can be replicated and be used in real life without needing like a lot of research funds. We decided to go with the Arduino series of microcontroller boards because Arduino comes with its own platform and IDE, so it has accessible open source libraries and a platform that is built for the Arduino. On the left, you can see that's the Arduino Mega Board. That's the controller board. That's the one that has the processing chips, and that's the one that is weaker computer of what will actually be needed to power like the camera, the GPS, and all these other applications, but to start powering the motors and like small sensors, it is enough to do that. And the board on the right, that's the shield, and you can see in red, those are digital signal inputs, and digital analog makes a difference, and in the green it's analog. And you need that shield board. Even though it's not really thinking, it's not really doing too much thinking, but it has an extended port so you can connect to the microcontroller board that does do the thinking, because you only get like maybe 2 hookups to the Arduino board, like 2 out pins for voltage, and you need a lot of sensors when you're constructing an autonomous boat. So that's the reason why shields are used. Okay, as I spoke about before, the signals, the tele 2 different signals, analog, I don't know if analog just seems to, when I think of analog, I think of the old rotary phones, just round, round, round. But that's pretty much it is. It's a continuous signal that is generated. It's a continuous measurement. So it's like always on, but because it's always on, you can think of sound waves, of course, voice in the air. And if you speak through anything or hum, you can get muffled because it's just continuous. It doesn't have a lot of ability to not be distorted through sounds and things like that. And it's not flexible in hardware design. These are the reasons. But I want to also tell you, analog was giving me good results because with the motor, the way I wanted to change velocities, it was a smooth continuous change, and it had a greater sensitivity to adapt to the velocity changes quicker and just quicker and more accurately. But because moving forward with all the digital sensors that are going to be required, it would degrade. It wouldn't be enough. It wouldn't be enough to power all the rest of the stuff and get it to work. Although just for the motor control, and that's where I'm at right now, it did give us the best results. But then as soon as we got the motors to work, the next thing, Wi-Fi, and then we had to go back to digital. So digital is a square wave. It's discrete sounds. You can think of computers. You can think of a lot of everything's digital now. But it's good because it doesn't have sound interference because it's like an on-off. It's rigid and bits, 0 and 1s. That's how the computers operate. It's flexible because of hardware. You can microchip. digital is just more common. Analog though is outdated, but it for just the motor move. So I'm just trying to say they have their own separate functions because I thought digital would be it, and then I liked analog, and then I kind of had to go back to digital because going for it. And here's a quick demonstration.
You have 1 minute to conclude.
Okay, yes. This is the motor configuration that I have designed for the boat using the propeller system, as I had explained. This is the Arduino 6 board with a sensor controller that is a microcontroller that I'm using to load my program.
Since she's frozen again.
No.
And other applications going forward. The process of starting the motors is to initialization of the code. I apply power back to the Arduino microcontroller board.
Yeah. Can you still hear us?
And I'm going to start it.
Lateshia, can you hear me?
Also, listen, I want you to select.
I think you're saying something we cannot.
Oh, you can't hear the sound? I'm sorry. Okay, well then that was just a demonstration, but going forward, I can just wrap it up. Going forward, I'm going to apply ESP 8266 Wi-Fi adapter. That's going to allow completely autonomous right now, because right now in the previous video you saw my computer was not controlling it, but it was hooked up to the actual Arduino board because it doesn't have Wi-Fi enabled on the board yet. So that's the next step. And then also going forward, that's a Pixels, that's a flight controller adaptation that's going to help with a lot of the camera, GPS, water depth perception sensors, a lot of different sensors. This is a radio controller, Tyrannus, but it's not part of the program, but because of the investment and time put in it, you need like a fail switch just in case for whatever reason the boat gets out in the water and the navigation system fails. I'll have a manual way to bring it back to shore. And that's a rough 3D sketch of what I'm thinking my hull is going to look like with propellers attached to it. And also because of Arduino choosing that platform, they have software that does really cool things. When I load my program to it, I can set mission points. I can have it tracked on this and take stats of like speeds, velocities, and things like that. So going forward, that's what I'm looking forward to working with. And I would like to thank you for your time and my acknowledgements and any questions.
This is very interesting. Are there questions? Just before your question, Lateshia, did you build the hardware and the software, or one of them?
Yes, I did. Yes, there is a program. I have some programs. I can programs. Yes.
Oh wow! Congratulations.
I was just wondering if she didn't mention the cost or the size of the actual.
Oh, the most expensive thing on there is the microcontroller board at $150. So everything that I've done so far with all of everything. Okay, I want to just say the actual stuff, not like solder and things like that you need to actually do other stuff too, but just like I'm talking about all the components, we're at like $400 right so far with the brushless motor. That motor costs like $13. The Wi-Fi board chip is $2. The Arduino Mega is $160. The Shield is like another $60. We have a couple cables. Okay, the battery supply. The battery supply was like $100 and something. The battery supply was pretty.
What is the size of the finished vehicle?
I couldn't hear the
What is
question.
the size?
The size of the battery?
No, the complete.
Okay, the boat. Dimensions that we're thinking about like 3 by 4 and maybe 3 deep or something like that. So something compactable, nothing ginormous, just something that can like hold itself in the water with lot of
Like
equipment
4
attached
feet?
to it.
Is it in feet or meters?
Meter, I'm thinking meters. We're going meters.
Okay.
3 by 4 by 3. 3 by 4 by 3.
Yeah, one more question. Yeah, go ahead.
So I had two things I wanted to mention. So I'm gonna be quick. The first one was, I wasn't sure if you had mentioned pulse width modulation. I remember
That
we were
is
discussing-
true. Yes, in the digital sound wave, that is you vary. Yes, you're correct.
Right, okay, so I just wanted to make sure whether or not you were using that or not, because that's a good way to transition from digital to analog. The second point was in regards to the Arduino board. There are third-party Arduino clones that would reduce your cost. So I know that, because I personally use them as well. Amazon has a few pre-made kits, and those kits were like, what, $60, $70? So that could be a good substitute if you'd like to reduce your costs.
This is true. And again, wanted to I know about those options, and I also know about the pulse width modulation, and you're very right, but I didn't even go through that with the pedometer and varying the speed to transform it. I actually just connected to the Arduino because that's the beauty of just having those ports. But also we went Arduino because it's just they're cheap enough, and there are cheaper boards, generics, but you need a little more skill sometimes when you run into an error instead of just going to the Arduino platform and things like that. So that's the reason why we wanted to keep it as broad and generalized as possible. So even though they are cheaper, you're right. I mean, come on now, but $120, they're cheaper. They're cheaper.
Okay, let us, well, sorry that we exceeded the time, but our speakers did a phenomenal job, so.